Hi everybody, and welcome to Lab 3. This is one of my favorite maps. I usually like to put little maps at the beginnings of these that I find that I really love, but this is one of my personal favorites. I love the criminal hideout and crazy hermit and evil spirits elements of this legend. I've been to many cabins where I could draw this same map of the surroundings, so I really appreciate this one. This lab is all about data, spatial data, and digging in, exploring it, figuring out the differences between raster and vector and seeing some of those differences, digging into the attribute tables and getting pretty comfortable with answering some really basic questions. This lab is kind of set up to help build the habit for you of going in and checking out what the coordinate system is, what the units are, what type of data it is, where is it stored, those kinds of questions that you should be doing every single time you get new data. You should be answering these questions for yourself right off the top. I apologize in advance for how disjointed this PowerPoint is. I try and just hit the things that I want to reiterate from the reading or things that I think apply specifically to ArcMap or the lab assignment, but the result is that it comes across a little bit schizo. So anyway, data, spatial data. We have two basic types, vector and raster. They look really different, they behave differently, they're manipulated differently, they have different sets of attributes. Everything about them is just inherently different. Vector data is discrete. We have points, lines, which are just a series of points with information on how to connect them, has a start and end, and if these start and end locations are in the same place, it creates a polygon. They are all based on sets of XY coordinates, and there's nothing in between. Vector data has great and elaborate attribute sets that go with it, which is, I think, where most of the power of vector data comes in. It's really good for mapping things that are discrete, like fire hydrant locations, or pipelines, or telephone networks, or voting districts, or property lines, things that are distinct in place and space and are surveyable. Raster data, on the other hand, is like a blanket that covers any kind of surface, and it's continuous. So it's a series of cells. It's a big grid that you can lay down on any surface, whether it's the surface of the Earth or in the atmosphere, precipitation, wind speed, solar radiation, things that exist everywhere. It doesn't mean that you have data collected everywhere, but it's stuff that does exist everywhere, like gravity or elevation or slope. That is data that's best represented with raster model. These are two images of the exact same area, but one is drawn up using vector data, polygons, lines that can be symbolized differently. This is a fault line. This is the Logan River coming out of Logan Canyon. Points that mark different locations. And then this is the same thing, just with a digital elevation model, a DEM that's just showing elevation. It does have a hillshade draped over it to give it some relief, but they really do look visually very different. Vector data, we refer to these as feature classes. They have different geometry types, points, lines, polygons, with different types of attributes associated with them. So each one of these is their own map. You can't have points and lines in the same feature class or layer, but you can obviously put points over lines over polygons in the same map project. But they are distinct map layers. These aren't in the same shapefile. They aren't in the same layer. They are individual maps that you can layer on top of each other in a project. And that's kind of the essence of GIS. The attribute tables, again, it gives you an identification field. It gives you an idea of what kind of geometry it is, and then the attributes that are associated with that feature class. In ArcMap, it looks very different, vector data, than raster data. This is your table of contents. This is the data frame, and these are the layers or maps, the individual maps that are brought into this map project. The symbols here illustrate that this is vector data. Raster data looks very different, and we'll talk about that in a second. A lot of information about these layers, about these individual maps, are found in the properties for these layers, and you can access that by right-clicking on any layer in the table of contents. And if we right-click here, it opens up a Layer Properties dialog box with a bunch of tabs. And in this lab, you're going to be exploring the Source tab and the Symbology and Display, playing with these a little bit. But this Source tab contains just an immense amount of information about this data. The first thing it shows you is the extent. These are the minimum and maximum values of the coordinates of this data. You can see the units are in meters. This means that this data is projected. If the units are linear or planar, like meters or feet, then this is projected data. If we saw DD here, or I think DMS, that would be degrees, and that's referring to a geographic coordinate system, which is three-dimensional, and the degrees are actually the angles coming out from the center of the Earth. So this is already telling us something very important about this data, that it is projected. If we look down in the data source information, the data type says shapefile feature class. Okay, that's good, that makes sense to us. The shapefile is the path. So this is sitting on my C drive, in this folder, in this folder, in this folder. This is the name of this shapefile, state US projected. Notice that it's different from the name in the table of contents. When you bring a layer or map into GIS or into ArcMap, you can change this. This is an alias. So you can slow left click on these and change what these read as to get rid of this jargon. But you're not actually changing the actual data. You're only creating a temporary alias that exists in this project. Okay, so this is good to know. If you're looking for data, sometimes these paths get broken and you need to repair it. You need to know where to find it. If you right click on this and go to the source, it shows you the path where this data is actually located, and it tells you the real name of the data, so you can go find it and add it to your map again. But I'm getting a little ahead of myself. The geometry type is polygon. That makes sense. This is the symbol in the table of contents for polygon shapefile. And then we get into some good stuff. The coordinate system. In a shapefile, it tells you it's a projected coordinate system. We're going to look at an example of raster data in a second, and they actually refer to the coordinate system as the spatial reference. I don't know why they do it differently, but it's just good to know that in a feature class, they just tell it like it is. Coordinate systems are built of two things, a datum and a projection, if the data is projected. If it's not, then the coordinate system is just based on the datum. This is a good example, but it tells you right here that it's a projected coordinate system. The projection is Lambert conformal conic, and it's built on this USA contiguous, which is sort of the geographic focal point. This is the area where it tries to minimize distortion. It's over the continental United States. Raster data. So you can see here in the table of contents, it looks very different. Rasters are typically displayed with a stretched color ramp. They can be classified, and we'll see some examples of that in a little bit, but this stretched color ramp is very typical of raster data. If we right-click on one of these layers or maps and open the properties, in the Symbology tab, we can see that this is displayed in a stretched fashion. It has the range of values, so 1340 meters elevation low, and our high elevation is around 2,900 meters. Those are the values that are here. Color ramps, whatever it happens to be, you can drop this down and there's 50 selections you can choose from. But they're broken up into like 250 different bins, and then this range of values is also divided up into 250 different bins, and then they're just assigned. So that's how you get this kind of display here. Every single bin on this color ramp has some elevation associated with each one of these bins. And then so each cell, which has an elevation value associated with it, is given some color bin on this color ramp. So the whole spatial extent of the data looks like this. Again, Logan Canyon and the Bear River Range. If we zoom way in, you can see that it's just a series of grid cells. Every single cell has one value. In this case, it's elevation because it's an elevation model. If this were a slope raster, the cell value would represent the slope for that exact cell. That cell size is really important. That's what we are talking about when we talk about raster resolution, that cell size. This is a map somebody made last year. You're going to be dealing with the same data set later in the semester. But we have a series of different resolution DEMs here, everything from a 2-meter LiDAR, and this means that each cell measures 2 meters on each side, 2 meter by 2 meter or 4 meters squared. There's a 5-meter autocorrelated DEM, 10-meter DEM, 30-meter DEM. We describe resolution in 2 dimensions. It's a 2-meter DEM, a 5-meter DEM, a 30-meter DEM, etc. You can see at the watershed scale it really doesn't make that big of a difference, but when you zoom in and look at a larger scale, you can see that the 30-meter really starts to pixelate and you lose a lot of definition. The most critical thing when you're building an elevation legend is that you must include units. It is impossible for your audience to know what this is. If it's feet, meters, there's no way for anyone to know, and therefore it has no significance. So if you're going to put an elevation legend on your map, make sure you include the units for your audience. The other thing is just to keep it simple. You don't need legend, Logan DEM value, high, low. These things are all just elevation. Keep it simple. include your units. If you can round these, and we'll talk about how to do that. If you want to take that extra step, this is really professional cartography. And we'll talk about hillshade a little bit later, but you never want to include hillshade on your legend. We'll talk about this later on. Underscores, jargon, make sure you edit this stuff out of your legends. RGB is what you'd see if you're displaying some kind of aerial imagery. You never want to include this on your legend. It just makes no sense and doesn't mean anything to your audience. And when you're dealing with spatial data, I want to make sure that you are doing all of your manipulations, copying, pasting, deleting, moving, reorganizing your data in ARC Catalog. If you view your data in Windows, this is the mess that you see. So look at here, we've got Little Bear Roads SGID shapefile. This is an alias that is equivalent to all of these different file extensions. All of these make up this. So in ARC Catalog or in ARC Map, this is what you see, and this is the safest way to deal with your data. If you needed to share data or were emailing data to yourself, if you drop one of these by accident, this file is corrupt and won't open in ARC Map anymore. So my recommendation is anytime you're moving or organizing data or deleting data, make sure you're working in ARC Map or in ARC Catalog. Avoid Windows like the plague. You are going to be asked about coordinate systems for the data in this lab. And I just want to remind you that there are two basic types of coordinate systems. There is a geographic coordinate system. It's based on a three-dimensional model of the Earth. There are literally hundreds of different kinds of geographic coordinate systems, whether they're globally focused, regionally focused. The underlying commonality is that they're three-dimensional, and they have units of degrees. And that's because they're angles coming out from the center of the Earth measuring latitudes and longitudes from the origin. Geographic coordinate systems can exist by themselves. So a set of data can just have a geographic coordinate system. The units are degrees. We also have coordinate systems that take a geographic coordinate system or a datum and flatten it to a projected surface. Projected coordinate systems always have linear units, meters or feet, and that's how you can tell it's projected. The coordinate system will usually include the projection in its name. But the most important thing is that the units are planar or linear. Units here are angular, degrees. Projected coordinate systems are based on geographic coordinate systems. They all have some three-dimensional model of the Earth as their foundation. So projected coordinate systems will also list degrees as their units. But when we ask you what are the units for this coordinate system, if it's projected, the linear unit trumps the geographic unit. So where do we find coordinate system information in ArcMap? The easiest and most straightforward way is in the table of contents. Go to your map layer, right-click, go to the properties, and open the properties tab, and use that source tab. So this is what a raster coordinate system is labeled as. It's called a spatial reference. You can see here that this is the name of the coordinate system. The linear unit says meters. The angular unit is degrees. So again, when we ask you what are the units of this data, the answer would be meters. Because it is projected, this trumps. This is referring to the datum. The datum is the three-dimensional model that this coordinate system is based on. It happens to be NAD 83, North America 1983, which is a regionally focused three-dimensional model of the Earth that's centered on North America to reduce the distortion in this area. The projection in this case is a universal transverse Mercator projection. These are 60 individual projections that go around the globe that reduce most of the distortion because it's a very small projection. Zone 12 is Utah. This is the one that we use here. Minnesota uses 15, Oregon, Washington use 10, just for an example. So the coordinate system itself, it's built of a datum and a projection, and those two things together equal the coordinate system. So if we were to ask you what the coordinate system of this raster DEM is, the coordinate system is NAD 83, UTM zone 12N, units are meters, period. If we asked you what datum this coordinate system is built on, you would say NAD 83, North American datum of 1983. So just a few suggestions. Save your work often as you're working. This will get more and more important as you go through the semester. ArcMap loves to crash. Make sure you keep your files organized. Use relative paths. Name your files meaningfully. Put everything in a deliberate place. Your labs walk you through this. And use ARC Catalog to copy and transfer your files. And then finally, the Lab 3 assignment is just to go through this. You aren't creating any kind of map or doing a screenshot. You're just answering a bunch of questions and then submitting those answers as your submission this week. So that's it.